Power engineering can indeed be considered a niche field. A niche, by definition, is a specific, specialized area within a broader industry or market. It typically involves focusing on a particular target audience, product, or service. There are several reasons why power engineering aligns with this definition. Firstly, specialized knowledge is crucial. Power engineers require specialized knowledge and training in fields such as electricity, thermodynamics, and control systems. This isn't the kind of knowledge you'd pick up in just any engineering discipline. Secondly, there's a specific industry focus. Power engineers work primarily in the power generation, transmission, and distribution industries. While electrical engineers may find themselves in a wide array of fields, power engineers are highly concentrated in these core areas. Thirdly, the technical nature of the work is a distinguishing factor. The work involves the design, installation, maintenance, and operation of complex power systems. This requires a deep understanding of electrical principles, equipment, and safety protocols. Fourthly, the field experiences reduced competition, because compared to broader engineering fields, the supply of qualified power engineers may be smaller. This can lead to better job prospects and higher salaries for those with the right skills and experience. Fifthly, specialized certifications are often pursued, because many power engineers hold industry-specific certifications, such as those from the Institute of Electrical and Electronics Engineers, or IEE, or the National Society of Professional Engineers, or NSPE. These certifications validate their expertise and demonstrate their commitment to the profession. However, it's crucial to acknowledge that power engineering, despite its niche characteristics, is a highly valuable field with broad applications. Electricity is essential to power our cities, homes, industries, and transportation systems. Without power engineers, we simply couldn't function in the modern world. Moreover, there is a growing demand for power engineers. The increasing electrification of society and the transition to renewable energy sources are driving this demand. As we move towards a more sustainable future, the need for experts who can design and manage efficient and reliable power systems will only continue to grow. Power engineers can find diverse job opportunities in various sectors, including utilities, consulting firms, government agencies, and research institutions. Whether it's working on the development of smart grids, designing renewable energy systems, or ensuring the reliability of the power grid, power engineers play a vital role in shaping the future of energy. In conclusion, while power engineering has niche characteristics, it also remains a critical and valuable field with strong job prospects. Its specialized nature and high technical skill requirements distinguish it from broader engineering domains, making it a rewarding career path for those with a passion for electricity and power systems. To elaborate on the technical aspects of power engineering, it is beneficial to delve into specific areas such as power generation, transmission, distribution, and protection. In power generation, engineers are involved in designing and optimizing power plants that convert various forms of energy into electricity. This could involve traditional fossil fuel-based power plants, nuclear power plants, or renewable energy sources such as solar, wind, and hydropower. The design process involves selecting appropriate generators, turbines, and other equipment, as well as ensuring the efficient and safe operation of the plant. Power engineers also play a role in developing new technologies for power generation, such as advanced nuclear reactors and more efficient solar cells. Transmission is the process of transmitting electricity from power plants to load centers, which are areas with high electricity demand. This involves the use of high-voltage transmission lines, transformers, and substations. Power engineers are responsible for designing and maintaining these transmission systems, ensuring that electricity can be transmitted efficiently and reliably over long distances. They also work on developing new technologies for transmission, such as high-voltage direct current or HVDC transmission, which can transmit electricity over even longer distances with lower losses. Distribution is the final stage in the delivery of electricity to consumers. It involves the use of distribution lines, transformers, and other equipment to step down the voltage of electricity and deliver it to homes, businesses, and other customers. Power engineers are responsible for designing and maintaining these distribution systems, ensuring that electricity is delivered safely and reliably to all customers. They also work on developing new technologies for distribution, such as smart grids, which can improve the efficiency and reliability of the distribution system. Protection is a critical aspect of power engineering. Power systems are subject to faults such as short circuits and overloads, which can damage equipment and disrupt the flow of electricity. Power engineers are responsible for designing and implementing protection systems that can detect and isolate these faults, preventing damage and ensuring the continued operation of the power system. These protection systems typically involve the use of circuit breakers, relays, and other protective devices. The work of a power engineer requires a strong understanding of electrical circuits, power electronics, control systems, and power system analysis. They need to be able to use computer software to model and simulate power systems, as well as to analyze data and identify potential problems. They also need to be able to work effectively in teams and communicate their ideas clearly and concisely. Furthermore, power engineers must stay up to date with the latest technologies and trends in the power industry. This includes renewable energy, smart grids, and electric vehicles. They need to be able to adapt to new challenges and develop innovative solutions to meet the growing demand for electricity. The increasing integration of renewable energy sources into the grid presents a number of challenges for power engineers. Renewable energy sources such as solar and wind are intermittent, meaning that their output varies depending on the weather. This can make it difficult to balance supply and demand on the grid, and it can also lead to voltage fluctuations and other problems. Power engineers are working to develop new technologies and strategies to address these challenges, such as energy storage systems, smart grids, and advanced control algorithms. Energy storage systems, such as batteries and pumped hydro storage, can be used to store excess electricity generated by renewable energy sources during periods of high output, and then release it during periods of low output. This can help to smooth out the variability of renewable energy sources and make them more reliable. Smart grids are distribution systems that use advanced sensors, communications, and control technologies to improve the efficiency, reliability, and security of the power grid. Smart grids can monitor the flow of electricity in real time, detect and isolate faults quickly, and optimize the operation of the grid to minimize losses and improve efficiency. Advanced control algorithms can be used to predict the output of renewable energy sources and to adjust the operation of the grid to maintain a stable and reliable power supply. These algorithms can take into account factors such as weather forecasts, historical data, and real-time measurements of the grid. The increasing adoption of electric vehicles is also creating new challenges and opportunities for power engineers. Electric vehicles can place a significant load in the grid, especially during peak hours when many people are charging their vehicles at the same time. Power engineers are working to develop new technologies and strategies to manage this load, such as smart charging systems, vehicle-to-grid, or V2G technology, and distributed generation. Smart charging systems can schedule the charging of electric vehicles to minimize the impact on the grid. V2G technology allows electric vehicles to feed electricity back into the grid, which can help to balance supply and demand and provide ancillary services. Distributed generation involves the use of small-scale power generation sources, such as solar panels and fuel cells, to generate electricity closer to where it is needed. This can reduce the load on the grid and improve the reliability of the power supply. Power engineers also play a critical role in ensuring the safety of the power system. They are responsible for designing and implementing safety systems that protect workers and the public from electrical hazards. These safety systems include grounding systems, protective relays, and arc flash protection. Grounding systems provide a path for fault current to flow back to the source, which helps to prevent electric shock. Protective relays detect faults in the power system and trip circuit breakers to isolate the faulted equipment. Arc flash protection systems are designed to mitigate the hazards of arc flashes, which are explosions of energy that can occur when there is a fault in the power system. The work of a power engineer is challenging and rewarding. It requires a strong technical background, a commitment to safety, and a desire to make a difference in the world. Power engineers are essential to the functioning of modern society, and they play a vital role in shaping the future of energy. The field of power engineering is constantly evolving, and there are many opportunities for innovation and advancement. Power engineers can work on a wide variety of projects, from designing new power plants to developing smart grid technologies to ensuring the safety of the power system. They can also work in a variety of industries, including utilities, consulting firms, government agencies, and research institutions. If you are interested in a challenging and rewarding career that makes a difference in the world, then power engineering may be the right field for you. To further illustrate the specialized knowledge required in power engineering, consider the area of power system protection. This involves the design and application of protective relays, circuit breakers, and other devices to detect and isolate faults on the power system. Understanding the principles of power system protection requires a deep knowledge of symmetrical components, fault analysis, and relay coordination. Symmetrical components are a mathematical tool used to analyze unbalanced faults on the power system. They involve breaking down the unbalanced fault currents and voltages into three sets of balanced components: positive sequence, negative sequence, and zero sequence. Each sequence component represents a different type of fault, and by analyzing these components, engineers can determine the type and location of the fault. Fault analysis is the process of calculating the fault currents and voltages that occur during a fault on a power system. This is essential for selecting the appropriate protective relays and circuit breakers, and for coordinating their operation. Fault analysis involves the use of computer software to model the power system and simulate the effects of different types of faults. Relay coordination is the process of selecting and setting the protective relays to ensure that they operate in the correct sequence to isolate the faulted equipment. This requires a careful consideration of the fault currents, relay characteristics, and the configuration of the power system. Relay coordination is essential for minimizing the impact of faults on the power system and for preventing damage to equipment. Another example of the specialized knowledge required in power engineering is the area of power system stability. This involves the study of the ability of the power system to maintain synchronism following a disturbance, such as a fault or a sudden change in load. Power system stability is a complex phenomenon that depends on a variety of factors, including the characteristics of the generators, the transmission system, and the loads. Understanding the principles of power system stability requires a deep knowledge of control systems, power system dynamics, and numerical analysis. Control systems are used to regulate the voltage, frequency, and power flow on the power system. They involve the use of feedback loops to maintain these parameters at their desired values. Power system dynamics refers to the behavior of the power system over time, following a disturbance. This behavior is governed by a set of differential equations that describe the interactions between the generators, the transmission system, and the loads. Numerical analysis is used to solve these differential equations and to simulate the behavior of the power system. Power engineers also need to have a strong understanding of the National Electrical Code, or NEC, which is a set of standards for the safe installation of electrical wiring and equipment. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Power engineers need to be familiar with the NEC in order to ensure that their designs comply with safety standards and to prevent electrical hazards. For example, NEC Table 310.16 specifies the allowable ampacities of insulated conductors rated up to 2000 volts based on the conductor temperature rating and the ambient temperature. Power engineers use this table to select the appropriate size of conductors for different applications to ensure that they can safely carry the required current. NEC Section 250.122 specifies the minimum size of equipment grounding conductors for grounding electrical equipment. Power engineers use this section to select the appropriate size of grounding conductors to ensure that the equipment is properly grounded and to prevent electric shock. NEC Section 430.52 specifies the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. Power engineers use this section to select the appropriate size of circuit breakers or fuses to protect motors from overloads and short circuits. Furthermore, power engineers need to be familiar with the standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. These standards cover a wide range of topics, including power system protection, power quality, and equipment testing. Power engineers use these standards to ensure that their designs meet industry best practices and to ensure the safety and reliability of the power system.